Hello, everyone. This week we are doing Lenz law. Lenz law is a little bit tricky, so I want to go over basic questions you can have here and just maybe do one exercise out of 3 in each part to show you how they are supposed to be done. We're going to start with part 1, induced currents. So there is a copper loop over here, and it's moved. It's either stationary or moving to the right or moving to the left, and they are asking if there is going to be any current in this loop from the point of view of magnetic forces exerted on the charges in the loop. What kind of charges we have in the loop? Well, we do have electrons, right? Electrons have negative sign, and they're asking if these electrons are going to feel the force from the field. Well, we know that when the charge is moving, there is a force, magnetic force. So the charge, velocity of the charge, cross product B with magnetic field B. So if charge is moving, there is a force. And they're asking what this force is going to do with electrons. Is it going to move them along the loop or kind of not move them or move perpendicular? I'm going to first answer the stationary case. Well, if the loop is stationary, there is no velocity, means that there is no magnetic force, right? Nothing is moving electrons. Now, I'm going to consider a case of the loop moving to the right. To the right, I mean this. Velocity of the loop is like this. Well, we do see that velocity and the field are both parallel. We do remember that for cross product, if vectors are parallel, the cross product is equal to 0, because remember the length of cross product is a length of this vector, and the sign of the angle between, and sign of 0 is 0. Well, you can answer similar way to the question of the loop moving to the left, because, well, it's just going to be opposite motion. Now, we are going to move to more complicated case, the field of a solenoid. What is different for this picture from the previous one? You see that field is not uniform in space. Not uniform mean that, for example, where the loop is located right now, we have 3 field lines going through the loop, right? But if we move loop, for example, towards the solenoid this way, for example, we move the loop this way, right? We are going to have these 3 lines inside of the loop, and maybe more lines which are coming out of solenoid, which are not drawn over here, but they are going to be, because the field is more concentrated where the lines are closer to each other. So you see that the field is not uniform. What I'm going to do, guys, well, I do see the arrow showing me the direction of the field. So I'm going to consider a top point of the ring, of the loop, and draw magnetic field at the top point. So over here, for example, imagine that we do have a positive charge. Well, I know that there are electrons actually moving around the loop, right? Not positive charges. But to make everything simpler, because positive charge shows direction of the current, I'm going to show the field B over here. Now, guys, remember that the force, magnetic force, is charge, velocity, cross product B. So how it's going to be directed? Remember, to find direction of the force, we will need to kind of turn our fingers of right hand. I'm sorry, I cannot show you the picture and my fingers at the same time. Fingers of the right hand from the first vector towards the second, and that's going to show you direction of the force. In this case, it's going to be hard to draw the force because force is going to be toward the page. I'm going to draw it like this. You guys remember that when we draw it like this, we mean actually that the force is looking like this, right? And this end is like a cross, because it's remember, it's arrow, and this end is like a dot. So sorry, it doesn't look like, I don't have any space here to show the dot. Let me erase this and just draw it one more time. Nicer. So this one is toward us and this one is from us, right? So actually the force is going to point towards the page, right? And the force on other not electrons, but I'm going to consider positive electrons, is going to, for example, if they are located here in the middle of the loop, like it's going to be down, and if they're located here, it's going to be up. It's hard to show like 3D picture here on 2D, like 2D picture, like show 3D directions. But if you just take a like pencil or two pencils actually, and point one pencil in the direction of magnetic field, one pencil in the direction of velocity, you will find out that the force is going to be up. What does it mean, guys? If you have some kind of positive charges in this loop, this force is going to move them up, and it's going to create a electric current, which is going to be like, let me show you the direction of electric current is going to be like this. Well, again, we do know that electrons have negative sign. For electrons, actually force is going to be down, right? It's going to create current of electrons going down, but because the electric current is motion of positive particles, we always draw it like in the positive direction, okay? So clear, right? Now, this was the case when the loop was moving towards the solenoid, so the current will be going up. And you can consider similar way the loop moving away from solenoid. I'm not going to do it. You can kind of draw the vectors and just imagine what is going to happen in opposite direction, right? Now they're asking for each case, you kind of, there is induced current, and we do see that there is no induced current when the loop is stationary. They're asking us to find direction of magnetic moment of the loop. Again, here, because you probably did not cover it in lecture yet, I'm going to show you what is magnetic moment of the loop. So if we do have a current along the loop moving like this, like on my picture above, like, so this part is closer to us, this part is further from us. So if you kind of curve your fingers in a kind of direction of the current, it's going to show you the magnetic field of the loop in the middle. And in this case, well, I don't know, like maybe I should draw how it's going to look like. I curve my fingers like this. Oh, does not look very nice, right? And my thumb is going to show direction of the field. So the field of the loop, which is created by this current, is going to go like in this direction, perpendicular to the loop and in toward the left. Okay, so now they're asking, is the loop magnetic moment is like coinciding with direction of the field? So I'm going to just draw it same direction. I'm going to label it M. Okay, magnetic moment is going to be coinciding with direction of magnetic field of the loop. Okay, whether the loop is attracted toward or repelled from solenoid, how to figure this out? Well, imagine that the loop is a little tiny magnet. If we want to label the poles of this magnet, what are going to be the poles of the magnet? Well, you know that the field goes like this. I'm going to draw actually like how the field is going to look like. Field is going to be like this, right? It goes like this. That's going to be the field B, right? We do know that the field goes out of North Pole, so I'm going to label that this side is North Pole and this side is South Pole. For example, over here, North is here and South is here, right? Now, attracted or repelled is going to be depending on like where are north and south pole of solenoids. For solenoid, well, I'm going to draw solenoid over here, really small solenoid, but that's a copy of the one which sits on the top. That's a copy of solenoid. Well, we see that the magnetic field of solenoid goes into it and goes out over here. So north pole of solenoid is here and south pole of solenoid is on this side. You see that what we have south pole of the loop and south pole of the solenoid. You know what is going to happen. They repel each other. That's how we answer the question here. Well, in the opposite case, that's going to be like maybe attraction, right? Now they're asking whether the force exerted on the loop tends to increase or decrease relative motion of the solenoid. Well, first, how the solenoid is moving in this case, which I'm considering. The solenoid is moving to the right, right? So it kind of, we are moving them closer to each other, towards solenoid. The repellence between south pole of the solenoid and south pole of the current induced in the loop are going to kind of try to move them apart. So what we are going to see, force exerted on the loop tends to decrease a relative motion of the loop and a solenoid, because loop is trying to approach solenoid, but the current which is created in the loop is trying to move the loop again back from solenoid. Okay, well, you can answer to the second question when the loop is moving away from solenoid like a similar way. Okay, it's just gonna be like maybe everything opposite. Now, guys, we are considering like these next 4 pictures, and they kind of asking us lots of questions about these 4 pictures. And what I'm going to do, I'm going to answer all these questions for case A, and I want you to try and answer all the same questions for case B. It's just like I don't know how to do the best way of explanation of this. So first, they're asking direction of the induced current through the wire of the loop. Well, how it's going to be? Let's just kind of imagine like how like everything is going to move. So the wire starts from this position and ends up in this position. Velocity is opposite to magnetic field, right? So I'm going to draw how magnetic field looks at this point on the top, just to find out like which way the force is going to be and which way the current is going to be. So that's magnetic field. I'm trying to just copy this arrow over here. It's not the same direction exactly, but because the line over here is going to be a little bit steeper, but that's going to be the B, right? Now, if we kind of right on the top point, if we move our right hand fingers from the velocity to B, Tom is going to show toward me. So the force is going to look like this. Well, on my 3D picture, it looks like it's just in a plane, but actually, if I draw it, actually, it's going to be something like this, looking toward me. The force is going to look toward me. So what kind of current this force is going to produce? And again, I'm considering a tiny positive charge over here. I know that it's wrong because electrons are actually moving, but it's going to be easier for us to define the current. Current is motion of positive charges. So what current is going to be? Like if the force is this direction, the current is going to be like that, right? Down. Let me just choose a different color and I'm going to label the current. The current is going to be like this. Okay, so now magnetic moment of the loop. Well, if the current is like this, magnetic moment is going to be this direction because the field of the loop, the field which is created by this current is going to be this direction, right? We kind of move it like fingers. Just use your right hand. It's hard for me to show my hand at the same time and point to this PDF file. So that's induced field B. I'm going to label it induced. Okay, induced field B. So again, magnetic moment is going to be a collinear to this one, induced magnetic field. I'm not going to draw magnetic moment here, but you can draw just similar arrow, label it with M. The area vector for each loop. Well, here, guys, area vector means that they kind of imagine that the loop is looking like this, right? And this is area. Right, we remember that area is perpendicular to the surface of the lake, which is covered. But this is our choice how we kind of point area vector. We can point it like to the left or to the right. Well, I'm going to point it to the left, and that's just like my choice. If you like to point it to the right, that's your choice. You can do it. It's not going to change anything here about the like conclusions. Okay, so I did point area vector. So area vector is like this. And again, in this case, you can point it opposite direction. Free to choose. The sign of the flux due to external magnetic field. External magnetic field. External is this. I'm going to label external. This field is external. What is the flux? Well, we remember that when area vector is coinciding with the field vector, the flux, which is like area by the field dot product, is going to be like positive. I'm going to label it external flux as positive, just because area is coinciding with magnetic field. In this case, same, just because area is still coinciding with magnetic field. So I'm going to just maybe write it down here. External is positive. Okay. Now, what else do they want? Sign of magnetic fields in both instances, and the sign of induced flux. Induced flux is due to this like induced field, right? Let me kind of change probably the color. So induced flux is going to be like in opposite direction because area vector in this direction and the B is in this direction. So induced flux induced is negative. Well, it's just like because the B is opposite to the area vector, this B, which is external B, induced B. Flux induced is negative. Okay, so I did draw everything for this like picture A, and you can do similar for picture B. Now they're asking us to use this picture and answer the questions. I'm going to make everything a little bit smaller because I cannot show you the picture at the same time and kind of like answer the questions. So they're asking like they're doing a dialogue of 3 students here or 2 students, no, 3 students here, and they're asking like students are making statements and they are asking us to verify whether they're true or not. The magnetic field due to the loop always opposes external magnetic field. Well, we did not do the second case, but so far we see yes, due to the loop is opposes, but actually in the second case you will find out that it's actually going to be opposite directions. So the first student is going to be wrong, but to show that he is wrong, you have to do case B actually. So far, case A is supporting actually first student, but again, I'm telling you that he is wrong. You do case B and you see that he's wrong, okay? The flux due to the loop always has opposite sign as a flux due to the external magnetic field. Well, again, you do need to do case B to show that student 2 is wrong. So far, yes, the flux of magnetic field and the flux induced are like opposite direction, right? Like one is positive, one is negative. But if you do case B, you're going to see that it's not necessarily going to be like this. It's going to probably be absolutely opposite. And case 3, the flux due to the loop always opposes the change of the flux due to external field. Yeah, this student is correct. Actually, the idea is that this induced flux is induced to oppose the change of the net flux through the loop. For example, you have like small flux here and your flux is bigger here. Why it's bigger? Because you see that field is more concentrated. So actually magnitude of the field is greater because flux is area by magnitude. Area is not changing, magnitude is increasing. So here the flux is bigger. So what the loop will try to do? The loop will try to create magnetic field, which is going to decrease the flux. So it's creating negative flux through, because actually the loop is increasing the flux. The induced current will try to decrease flux. But if you are decreasing flux, magnetic field induced current will try to increase it through making up this current. So it looks like the loop is trying to resist to change of the flux. So I'm going to write it down over here. So I'm going to write it down like over here, like change of the flux external is opposite to flux induced. It looks a little bit like crazy, right? That this flux and this is change, but that's how it works. So it's not very important what was initial external flux and what was the final external flux, whether it's positive or negative. The induced flux is going to oppose the change. So if it was negative, but it kind of increased, it will try to decrease this if it was. So it does not matter actually what was initial or final here. It's important what was the change of the flux. We are going to see it on the last page of this tutorial. Okay, I'm going to move to the next page. And well, again, you will need to finish case B to kind of tell why the students are wrong over there. Like, okay, next page, page 3, is telling like how Lenz law is going to work, and they're considering a different case. Before, it was very obvious that like current is created because electrons are moving, right? There is a force, the force is moving electrons and current is created. Here, guys, nothing is going to move. The loop is stationary. The only thing what is changing is field B. Imagine that field B looks like this, B0 by cosine of t. Everyone remembers how cosine looks, right? Cosine looks like this. So cosine looks like this, but let's imagine that we consider only this part. you see that B over here is decreasing. Again, as an example, it's not necessarily changing by cosine, but just an example. So you see that B is decreasing. So again, here nothing is moving. The loop is stationary. So we cannot explain anything here with electrons moving and creating electric current. But actually, the law is going to stay, because when you change the field over here, what is going to happen to the flux? Flux, which is area multiplied by electric field, magnetic field. When you kind of decrease B over here, it's going to decrease flux. So there is going to be the change of flux. And it's still going to create a current here, though nothing is moving. Well, if you consider student 3 who tells that flux created is opposing the change of the flux, that's going to be like application of this. Okay, and they are asking like, it is observed that there is a current induced through the wire of the loop in this case. Use the appropriate reasoning above to find direction of the current through the wire. Let's do this. Let's try to find direction of the current through the wire. So we know that, well, let's set up area vector like this, just to like, so the flux is positive here, but it's decreasing. So what is change? I don't know. If it's decreasing means that like for over here, for example, it was bigger, over here is smaller. The change is like this, and this change is negative because you kind of subtract something to get from this point to this. So the change is negative. What will induced current do? Induced current must create induced flux, which is positive, right? To compensate for this change. So we have less flux, so induced is going to create more flux. More flux means the flux is positive. Flux is positive when area vector coincides with B vector. So what kind of B vector is supposed to be created by this current? We don't know how the current is going to look, but we can predict the B vector, right? Because we're supposed to create it positive. Positive means that area and B are going to be same direction. So I'm going to draw this. This is going to be B induced. Same direction as area, just to compensate for the change, right? Now, which current can create this B induced? Well, imagine that your thumb is looking over this B induced. What kind of curve you are going to have over your fingers? The curve is going to go like this, from this side like that. Okay, so that's going to be induced current. I'm going to label it. It's a bit hard to do all this stuff with, like, you know, on the page, right? Now they are just kind of explaining how Lenz law is working. So we basically answer all these questions, all these questions, and we are moving to the last page. Last page is a little bit tricky here, guys. What we have not changing magnetic field, right? But we do have the loop, and it's rectangular loop, and it's moving toward from the region with no field into the region with field. Okay, and they're asking us some questions. I want to kind of briefly explain what is going to be here. Well, they show two instances, instance t equals t0 and instance like delta t seconds later. So kind of the loop moved inside of this region with magnetic field, right? And they're asking, what is magnetic flux through the loop due to external field, positive, negative, or zero? Again, to find magnetic flux, first, we're supposed to define area vector because flux is area vector multiplied by the field vector, right? To find the flux, we'll need to know which way area vector. Well, I don't know, guys. You see that field goes into the page, actually, right? We see crosses the field B is into the page. Well, I want to make area vector looking toward us, out of the page. But again, when you do it, you can point at any direction. So my area vector looks exactly toward me. Now, what is the flux in this case? Well, the flux is going to be negative because these two vectors are opposite direction. How to calculate the flux? Guys, I'm going to do it a very primitive way. I'm just going to calculate crosses. There are three lines, right? 1, 2, 3. So I'm going to write down the flux here is equal -3. Well, it's not very important, -3 of what? Because at the end, we just need to find the sign. What is going to be the flux at this moment? Well, because area vector and B are same direction, it's going to be, well, I'm going to label flux 1 here and flux 2 here, okay, just to make a difference. We have more crosses, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 crosses. So it's -9. What is going to be the change of the flux? The change is final flux minus initial flux. So it's -9 minus -3. And in my case, it's going to be what? -6. So the change is negative. Well, if you direct your area vector opposite direction, it's going to be positive. It's not going to change the very final answer, but it's going to change the like minuses and pluses here. So in my case, the change is negative. But again, it depends on how you direct area vector. Use Lenz law to determine whether the flux due to the induced current in the loop is positive, negative, or zero. Well, we know that the change is negative, so the flux induced is supposed to be positive, right? To compensate this change. Just because if this one is negative, we're supposed to get positive to compensate this. Well, what is direction of the current in the loop during this time interval? Now, guys, to find direction of the current, we'll need to find what kind of field is going to make induced flux positive. I'm going to use a different color of the marker, like blue one, okay? We need a positive, so we need the field B collinear to a vector looking toward us. So the loop is going to create field B. I'm going to draw it over here, okay? It's going to create field B, which is supposed to look toward us. I'm going to label it induced. That doesn't look very nice. Okay, guys, I'm sorry. I'm going to write it down next to, I'm going to draw the field over here, but label it over here, okay, just like not too messy. So that's going to be the field to create positive flux, induced field, right? Now, well, it's kind of logical, right? We kind of create the field B going from us. The loop wants to have it like almost zero, so it's creating opposite direction of the field. Now, how the current's supposed to go? Well, again, use a right-hand rule. Put your thumb along vector B, and your right hand supposed to show you direction around the loop. So my direction is like this. So the current is going to be going counterclockwise. If you change direction of the area, everything is going to change here, and you're still gonna get the same current. That's a trick too. So the direction of area vector does not affect the direction of the current. Okay. Well, you can just answer that it's counterclockwise, or just draw the picture how the current is going to look. The current is going to look like this. Okay. Now, tricky question D. Loop continues moving inside of the field. Do you see that the flux is changing between T1 and T1 plus delta T? Well, 1, 2, 3, 4, 1, 2, 3, 4 crosses. So we have equal amount of crosses here and here. So between these two motions, the net change of the flux is equal to 0. What does it mean? It means that by Lenz law, the current induced in the loop is going to be 0. So actually, interestingly, the current is going to be induced in this loop only while it's moving from no field region into the field. As soon as it moved inside, there is going to be no current in the loop. Okay, the loop is going to be kind of give up, let's say, on resistance. It's going to stop resisting. Okay, guys, I want you to maybe kind of make a conclusion. If the change of the flux equals to 0, then induced flux is also 0, right? What is going to be the current then? Answer this question yourself. And for discussion, I'm asking you to discuss last question. The students are talking about like what is going on in this exercise. So please discuss them in the discussion, okay? Okay, that's all. I'm hoping that this video is going to help you. I'm also planning to put a little video or two from YouTube where people are explaining Lenz law, because my videos are not that super good. But otherwise, thank you for your attention, and I'm sorry that it looks so long.